Yet another way of doing the enthalpy balance for this type of reaction is to, since we are not, the reaction's not at the standard conditions that the heat of reaction is given, well, we can change the heat of reaction to be for one of the temperatures that is involved in our process. So we're feeding at 75 degrees C, and products are coming out at 300 degrees C. I am going to choose to use the gases at 300 degrees C as my reference condition. So the reference condition I'm going to use is 300 degrees C and gases. Now that means that if I use this, well then all the enthalpies of the products are going to be zero. This also means that all the enthalpies of the reactants are going to be negative, but that's okay, it doesn't matter. But I do need to correct the heat of reaction for to be 300 degrees C instead of 25 degrees C. So what I'm going to do is create a hypothetical path. And I've got we got 4, let me just write symbols here. 4A plus 5B goes to 4C plus 6D. Now, these are all gases, so I'll write that down, all gas. And what we want is the heat of reaction at 300 degrees C. Well, we don't know that, so I'll just put delta HR, and this is going to be at 300 degrees, and this is going to be at 300 degrees C. And so I'm going to create a hypothetical path where I take the I'll take the reactants to 25 degrees C, so same things here at 25 degrees C, and then I will react them. This is all done at 25 degrees C, and I know what that heat of reaction is. This is my heat of reaction at standard conditions. And then I'll raise the temperature of these products to 300. So, the first leg of the journey here is the enthalpies are going to be the inlet temperature, or the starting temperature, going to 25 degrees C of Cp dt of the gaseous heat capacities. And then over here we will have the integral from 25 to 300 degrees Cp dt for each chemical. And then, of course, times the stoichiometric coefficient. Now, if the heat capacity of our products is the same as the heat capacity of our reactants, then this leg and this leg should be the same. And that's typically they're close because the heat capacity is all due to vibration and stretching modes of the atoms in a molecule. And when we change reactants to products, generally the number of bonds that absorb this energy is pretty similar. And so it's not unusual for these two legs to be fairly close to each other, which means that the heat of reaction at one temperature isn't much different than the heat of reaction at another temperature. But it might be, and so we need to calculate that. Now I'm going to go to another screen to show you the calculation because it won't fit here on this screen. So the heat of reaction at 300 degrees C is equal to the enthalpy of the reactants going to from 300 to 25 degrees C and so that will be 4 molecules of ammonia, so I'm going to say 4 times CPA dt plus 5, because there's 5 oxygens, going from 300 to 25, of CPB, the oxygen dt. Now I'm going to add to that the heat of reaction. That's the second step in our hypothetical path. This is the heat of reaction at standard conditions. And now I'll add the sensible heat changes of the products. So they're going from, let's see, there's 4 nitric acids, and it's going from 25 to 300. CPC dt plus 6 times the integral from 25 to 300 of CPD, the water, dt. And if you look at the enthalpy table then, or this sheet, which has the tab corrected DHR, you'll see that the heat of reaction at 300 degrees C I calculate to be minus 899.9 kilojoules per mole, and compare to the given, which is 904.7 kilojoules per mole. That was at 25 degrees C, and this is at 300 degrees C. So you see they're not really terribly far apart, but that's how you would correct them. Now that becomes your reference state, 300 degrees C and gases. And so if you look at the enthalpy table on the corrected DHR tab, you'll see that they are all 0 because they are at the reference condition. And all of the enthalpies of the inlet materials are negative because they're at a lower temperature, and in the case of water, a lower state of aggregation or phase, so they're quite a bit lower and negative. But the calculation yields, still yields, let's see, Q equals minus 2861 kilojoules, which is the same as all the other calculations. So we have four types of calculations here, all valid, all coming up with essentially the same number as should be. So you should try to become expert at using all 4 of these methods, because on an exam I will specify which one you need to use. So use my spreadsheet as a kind of solution manual for this calculation, and try these calculations yourself. Do as many of the hand calculations as you can so you become quick and accurate making these calculations, so you don't have to spend a lot of time thinking about how to do it. You are experienced and know how to do it quite quickly and can spend your exam time on more difficult concepts. So, as always, have fun.